Lab M03. There we go. This is Robert Gon Lab M03 with Greco. This is Lab 9 at home. So in this experiment, we looked at the motion of a mass spring system where the mass swings in an arc while it's also oscillating on the spring. I want to preface this whole thing, by the way, by saying that it's a little loud in the background because I'm at North Ave, because I have a situation in my dorm, and I can't go back right now, if you know what I mean. We looked at two-dimensional motion, used fundamental principles to predict the motion, used the momentum principle as a position update, and then used Newton's second law and the principle of thermodynamics. Here's our code for the initial position, and just the code actually itself, but all the initial conditions we used, we came up with on our own, basically, based on the tracker video. We were supposed to get as close to the video motion as possible, and then we also ran a second ball, which ran based on the exact data we got from tracker. And so we'll run this, and hopefully this runs. Sometimes it runs really slowly while I'm recording. Yeah, so we're gonna wait. Okay, it's going. And you see the orange ball is the ball from our simulation. The blue ball is the actual motion. You see at the end right there, they started to vary a lot, whereas in the beginning they were staying closely together. But if you look at the graph, really they weren't ever exact. And this is because this is such like a volatile motion that after a while you can't predict what's going to happen because there's so many forces acting on it from all different angles. The blue ball represented the weight, the orange ball was the simulated mass. Our blue ball was the tracker video data, and then the green line was our model, red line was simulation. We saw that they varied. Yeah, and we did 6.96 newtons per meter as the stiffness, and 1.334 meters as S. We used Hooke's law to find that. Static equilibrium, the spring length is 0.7 meters. We used graphs to find the period of the oscillating masses in the x and y directions. And to find the difference, we did the final time minus initial time. So let's go into what does it mean. We compare the period of oscillation found from examining x component position, period of oscillation determined from the y component. Do they differ? If they differ, can you explain why? For y oscillation, we did the model minus the minus 2.97 minus 1.479, got 1.492 seconds. Simulation minus 2.891 minus 1.409. We got this from our tracker data and from our code. And 1.482 seconds. Difference is 0.01 seconds. Barely differ. So same with x oscillation. This is the wrong difference, but as you can see from here and here, the difference is very small. So number 2, with your new choice system, determine the work done by the surroundings. Is energy principle satisfied? The new system includes the ball, the earth, and the spring. So there are no outside significant surroundings. In lab, we didn't have, I think it was the spring included, so there was work done, but with this system there's no work done because the surroundings that we had in lab are now included in the system. So for work to be done, energy has to leave the system and go into the surrounding object. That doesn't happen here because all these things are included in the system. And the energy principle is satisfied because the change in energy is 0. So yeah, the energy just stays in the system. Number 3, I'm not going to read for the sake of time, but we all know what it is. And here's what we did. So origin change, the sum of all the energies will be less than the sum at the original location. And this is because potential energy has to do with interacting objects. So you can get different values based on your origin choice. The physics of the system doesn't change, and the change in energy quality stays the same. And in conclusion, the lab agrees with energy principle, Newton's second law, and the conservation of energy. The change in energy is equal to the work done by the surroundings. So when we include the earth, ball, and spring, the delta E is equal to 0. and so changing the origin didn't change the physics for that very reason. And that's it. Thank you.